Okay, so first off in this session, we have Erin Hicks from the University of Alaska Anchorage, who will be telling us about the Kona survey, distribution and kinematics of the circumnuclear stars, molecular gas, ionized gas in local Seyfert galaxies.
Thanks, Vivian. So I start by thanking the organizers for the opportunity to share the science with you, and by thanking my collaborators in the Kona survey. Right, so the Keck OSIRIS nearby AGN survey consists of 40 representative AGN. These are AGN we've observed in the K-band with OSIRIS and adaptive optics. The adaptive optics allowing us to reach down to scales of tens of parsecs and probing the molecular hydrogen, the stars, as well as ionized gas in the circumnuclear region. And by circumnuclear, I mean the central 400 parsecs or so. Here's an example of the molecular hydrogen we've measured in several of these galaxies, shown as the flux, the velocity, and the velocity dispersion. And generally, we can say that for the molecular hydrogen traced by that 2.12 micron line, we see this emission throughout the circumnuclear region. We see a lot of variation in the structure seen in that flux distribution. If we take an azimuthal average of that flux distribution, we find that typically the half-width half-max of that central emission is about 35 parsecs. And of note is that the Kona survey has 20 Seyfert type 1s and 20 Seyfert type 2s. So we're able to compare these two subsamples. And we don't find any difference in these two subsamples as far as the flux distribution goes for the molecular hydrogen. And looking at the velocity dispersion, we find it's relatively low in the molecular hydrogen, around 60 kilometers per second. And again, no difference between Seyfert 1s and Seyfert 2s. And we see this is lower than what we find with the circumnuclear stars, which is hovering around 100 kilometers per second. And I'll note that although the kinematics suggests that the molecular hydrogen is generally dominated by rotation, there are significant signatures of inflows and outflows in many of these galaxies. We also measure the ionized gas traced by the silicon-6 line, as well as bracket gamma emission. And what we find for this sample is that the ionized gas is more centrally concentrated. We also see it's structured a cone structure in many of these cases. When we, again, take the azimuthal average of that flux distribution, we find the half-width, half-max in these galaxies is more like 25, 26 parsecs. So suggestive potentially of a different ionization mechanism for the ionized versus molecular gas phases. Looking at the velocity dispersion, it's significantly elevated for the silicon-6 line as well as for bracket gamma in comparison to what we see for the molecular hydrogen. In this case, we actually see that the Seyfert 1s shown in blue here and Seyfert 2s in green, and the dashed lines in the background are the individual galaxies. So what you're seeing as a solid line is the average of all of the galaxies in that Seyfert 1 subpopulation, for example, for the blue. And what we see is that the Seyfert 1s tend to be a little higher in velocity dispersion of the silicon-6 line than what we see in the Seyfert 2s. And again, the fact that the dispersion is higher, it's just that this ionized gas is involved in an outflow, whereas we see the molecular hydrogen is primarily dominated by disk rotation. And as a first step towards analyzing the kinematics in more detail, we determined the global kinematic position angle of both the stars as well as the molecular hydrogen. So the stars are shown on top here. We symmetrized the fields to determine what the global kinematic position angle is. And then shown in that the right-hand side is the residuals. So subtracting that symmetrized field from the measured velocity field. And this gives a measure of, one, how well the assumption is that rotation is dominating that velocity field. The residuals represent those non-circular motions that are present. And what we find when we compare the kinematic PA for these stars in the circumnuclear region to the large-scale photometric axis determined from K-band imaging with 2-mass is that there's general agreement, so that the circumnuclear stars are aligned with what is seen in the host galaxy. Interestingly, when we look at the residuals of the circumnuclear stars, so again, subtraction of that symmetrized field from the measured velocities, we see those galaxies that tend to have a higher hard X-ray luminosity are those that have higher residuals. So suggestive perhaps of the feedback to the stellar component in that circumnuclear region. Looking at the molecular hydrogen and comparing the position angle determined from the kinematics measured of the gas to that of the circumnuclear stars, we see that in many cases there's good agreement, but in many cases there's not. So in about half of the galaxies, there's a significant offset in the position angle determined from the molecular gas compared to the stars. And again, there might be a suggestion that there's a higher degree of residuals after subtracting that symmetrized field from the measured velocity of molecular hydrogen in those galaxies with a higher X-ray luminosity. So again, suggestive of feedback in those cases, greater degree of feedback. I'll just give you a bit of a glimpse as to work to come, a more detailed analysis of those kinematics. The OSIRIS field of view is rather small, and it's very, very helpful to place it in the context of what's going on at larger scales in the galaxy. And we've done this through looking at dust structure maps from HST as well as H-band imaging from NERC2 with AO. And in this case, this is Markarian 1066. You see in the dust structure map here, the white represents outflow. So the outflow axis is up and down in this image, which aligns well with what's seen in the bracket gamma emission, as well as the molecular hydrogen in this case. And then the dark regions of the dust structure map represent dust. And so typically associated, often associated with spiral structures. So we would expect inflow along those structures. And in 1066, there's suggestion of this. So just kind of crudely marking out where that inflow might be expected and then mapping it onto where we would see it. You can see, for example, in the molecular hydrogen here, there's enhanced velocity dispersion in a region where there's actually both inflow and outflow potential to be occurring. Looking at the velocity fields of the molecular hydrogen here, you can see that there's a lot more going on than just disk rotation. Fitting kinemetry, this map on the left-hand side represents a non-circular component of that velocity field. And you can see there's significant non-circular motions in the region where both outflow and inflow are occurring. So there's a lot of detail in these kinematic maps to characterize the inflow and the outflow. So let's leave you with my summary slide here. And we find general agreement of the circumnuclear stars in terms of their kinematic axis with that of the large scales. We see the molecular hydrogen throughout the field of view in the circumnuclear region with a relatively low velocity dispersion. The ionized gas is more centrally concentrated with a higher velocity dispersion, indicative of outflows. And I also mentioned that we've measured or estimated the total gas mass from what we see of the warm molecular hydrogen. And what we find through this is that there's a lot more gas sitting in that central region. There's a large reservoir of gas, 10 to 1,000 times more than is needed to feed the AGN that's sitting in the center. So there's a lot of gas in that circumnuclear region. And I'll leave it at that.
Thanks, Erin. I actually have a question for you. So, well, actually, I see a question coming. I'll ask that one first. So, Lee Armis is wondering if you can say anything about the variations in the stellar ages in the center via the CO band heads and how this might compare to the outflows.
So I would love to be able to say yes to that question. Unfortunately, no, we don't see any significant variation with the signal to noise that we have with the CO band heads. That detailed analysis is not one that can be done for the whole sample. Maybe on individual cases where we're measuring the CO band heads, well, there might be something to be said there. But there is significant effort put towards getting optical imaging, not of the Kona sample, but of other samples I'm working with that have some overlap with this sample. And so using optical IFU data, we can address that kind of question more thoroughly.
Thank you. Now I can ask my question. You mentioned essentially the silicon-6 essentially concentrated in most cases. Were they actually well fitted with a single component fit, or did they actually have any broad components that might be associated with the outflows?
To the emission line structure?
Yeah.
Right now, all that's been done is a single component. In a few cases, there is evidence that I think multiple components would do a better job. But I would not say that in general is the case for this sample, that generally a one Gaussian fit does the job well.
Okay. Let's see. I guess we're actually out of time in the questions. So if there's any other questions, please move over to the Slack channel.